Now let's talk about events involving random vectors. In the general sense, events involving a random vector of size n will be subsets of R to the power n, the n-dimensional space, let's say. Uh, for random variables, well, our space or sample space was the real line. So the events regarding that random variable was subsets of the real line. Okay, for instance, just a point like x equals some value 5, or intervals x being between 3 and 5, okay, or just x being less than 5, x being greater than or equal to -3, etc. So those are all subsets of the real line R. But here we are talking about the n-dimensional space. So generalize that approach. Events now are subsets of R to n. Here I'm giving examples for n equals 2. So we have just a two-dimensional random vector. The components are x1 and x2. Here you see the event x1 plus x2 less than or equal to 10. So you see this line here is the x1 plus x2 equals 10 line, and all points below it are in this event. If you have like x1 plus x2 greater than or equal to 10, you would have this region. If you do not have equality, if you have strict inequality, then you would remove the line, okay? And that might change the result, the probability, in case you have some probability mass lying on this line. Very similar to the mixed type distributions we talked about, random variables. Here again, in the second one, you see an event. Well, the minimum of x1 and x2 is less than or equal to 5. You see, this is the region where the minimum of the two is less than or equal to 5. Or this one, x1 square plus x2 square is equal to 9. Now you have equality here. So the set described by this event is that just the circle, okay? Not the outer region, not the inner region. They are excluded because we have equality. So just the circle is the event here. Okay, and unless you have some probability mass lying exactly on the circle, the probability of this event would be 0 if you have a continuous distribution on this two-dimensional space. Okay, now we will next look at the ways to describe distributions of random vectors. As we did with random variables, we will talk about the probability mass function, but now we have joint distribution. So we'll talk about joint PMF and joint CDF and joint PDF. And the joint PMF is defined in case you have a discrete random vector where you have all components being discrete random variables. So the joint PMF P sub x is defined as, well, this is an alternative notation, the probability that the random vector x equals the parameter x. This parameter here, you see, it's a parameter of, it's a vector of parameters. Okay, so I can represent it like this in handwriting. It's just x1, x2, a vector of values, parameters, not random variables, but just values. Okay, so this is the definition of joint PMF. As you see, it's very similar to the definition of the PMF for a random variable. We just extend the definition of PMF to a higher dimensional space. And here you see, we just generate, well, we just expand this definition. Well, random variable x being equal to parameter x, this event is equivalent to the first component being equal to the first component of the random variable being equal to the first component of the random, the parameter vector, and not or, but and the second component also equal the second component of this vector, and finally the final component equals the final component. So you see, this is a joint event. This one intersection with this one, intersection with this one, all of them intersection. Okay. So this is the definition of the joint PMF. Well, the joint PMF is a PMF. Okay, so it carries all the properties of the PMF we have all known before. Therefore, first of all, it's a non-negative function. For whatever value it takes, it cannot take negative values. And when you add it up with respect to all possible parameter combinations, you should get a 1. Now here, this is a vector. So in fact, while you see a single summation here, this entails a number of summations. Okay. In fact, n summations when the dimension is n. And when you define the joint PMF in this way, probabilities of related events, as we have seen earlier, can be written in terms of the joint PMF. So probability of an event A can be written as, well, the sum of the probabilities for which the random variable falls in this event, which defines a subset of the space R to N. Okay, so you add the PMF value for those events, you get this probability.